In this video, we want to look at the first two of the gas laws for this chapter, Boyle's law and Charles's law. Boyle's law looks at the relationship between pressure and volume. Here's some sample data that's from your textbook of pressure versus volume. Pressure here is in inches of mercury and volume is in inches cubed. You can see that as the pressure is increasing, going down this first column, the volume is decreasing. So in this case, we're increasing. As we go down here, we're decreasing. When you multiply those two numbers together, the actual number that you get, rounded to three significant figures, is 1.40 or 1.41 times 10 to the third. So we have a relationship here between pressure and volume, and we see that it's an indirect relationship, whereas one variable increases, the other variable decreases. And this is Boyle's law, discovered by Robert Boyle, describing the relationship between gas volume and pressure. As the pressure of a gas increases, its volume will decrease, as long as we hold the temperature and the total amount of gas, the total number of moles, constant. There's an inverse relationship between pressure and volume. The equation that we can come up with is P1 times V equals a constant, K, which many times we'll write in a simpler form, P1 times V1 equals P2 times V2. This is a form that allows us to solve more easily for changing pressures and volumes. It does not matter what units the pressure are in as long as they're the same on both sides of the equation. It does not matter what units the volume are in as long as they're the same on both sides of the equation. Understand here that temperature and moles are constant. So if the temperature is changing or the number of moles are changing, then we cannot use Boyle's law. So if we move to some example problems, I'd like you to try these problems on your own and then press play and see the correct answer. If the pressure exerted on a gas in a 20.5 liter weather balloon decreases from 1 atmosphere to 0.562 atmospheres, what is the volume of the balloon? So we've got P1 V1 equals P2 V2. The pressure, 1.01 atmospheres. The volume, 20.5 liters, equals the new pressure, 0.562 times volume 2. So we're going to do 20.5 times 1.01. We get 20.705 equals 0.562 V2. Divide by 0.562. We get 36.8 as our new volume. Now, we can check to make sure this makes sense. The pressure is decreasing, so the volume should be increasing. It decreases by a little bit less than half, so the volume should be a little bit less than double, and that is indeed the case here. What pressure in atmospheres is required to compress 1 liter of gas at 760 millimeters of mercury pressure to a volume of 50 milliliters? So, P1 V1 equals P2 V2. So we got 760 millimeters of mercury, a volume of 1.00 liters. We're looking for the new pressure. We need to have the same units, so I convert this to liters, 0.0500 liters. So I get 760 equals 0.0500 P2 we're going to have to increase the pressure a pretty dramatic amount, which is 1,520 15,200 millimeters of mercury. Now we want the answer in atmospheres, so I have to convert this to atmospheres. The other thing I could have done is convert the original number to atmospheres, but it doesn't matter whether you do it before the problem or after solving the problem. So there's 760 millimeters of mercury per 1 atmosphere. We get 20.0. All the original numbers had 3 significant figures. So 20.0 atmospheres. So Boyle's law, inverse relationship between pressure and volume. As the pressure increases, the volume decreases. Now before we can move into Charles's law, we've got to talk about temperature. Temperature, we know, is the relationship, the proportionality to the speed at which the particles are moving. The faster the particles are moving, the higher the temperature. We generally use the Celsius temperature scale in class. However, we need to add in another temperature scale known as Kelvin. The Kelvin temperature scale is just like the Celsius temperature scale in that the difference of 1 degree Celsius is the exact same amount. It just has a different starting point. If you think of the Celsius scale, we have 0 degrees Celsius, which is the freezing point of water. We have 100 degrees Celsius, which is the boiling point of water. Now, the Kelvin scale is a similar scale in that there's a 100-degree difference between those 2 points. We just do not have any negatives in the Kelvin scale. You start at the absolute lowest at 0. 0 Kelvin is what's known as absolute zero. It's the point at which all substances stop moving, possess no heat. In the Celsius scale, this is actually the point of negative 273 degrees, known as absolute zero. The difference in the Kelvin scale is we set that point as 0, which means the freezing point of water is 273 degrees Kelvin, and the boiling point is 373 degrees Kelvin. The conversion from one to the other is what's listed in the equation here on the screen. The temperature in Kelvin is the temperature in Celsius plus 273. Now, Charles's law looks at the relationship between volume and temperature. Gas particles, if they're moving faster, are going to take up more space, not less space. So there's a direct relationship between volume and temperature. You slow the gas particles down, they come closer together. You speed them up, they get further apart. If you're holding the pressure constant, now we have to have a constant pressure for this to work. If you do a graph of temperature versus volume, this is the graph you'll see. It's a straight line, sloped upwards, positive slope, direct relationship. You'll notice that they all work back to negative 273. You'll notice many of these are dashed lines because at those points they actually form solids or liquids and therefore do not behave as gases. But if you extended the line backwards, it would all meet at negative 273. So the formula for Charles's law, being a direct relationship, is kind of the opposite of the formula for Boyle's law. V1 over T1 equals K, so the volume over temperature equals a constant, which we can rewrite. V1 over T1 equals V2 over T2. It does not matter what volume units you use as long as they're the same. Temperature must be in Kelvin. Doesn't matter if you want to solve for degrees Celsius. If you have degrees Celsius to start with, you must convert to Kelvin before doing Charles's law. Then you can convert back to Celsius, but you cannot start at Celsius. So let's look at some example problems. A sample of neon gas occupies 266 milliliters at 25.2 degrees Celsius. At what temperature would this volume be reduced by half? So V1 over T1 equals V2 over T2. So our volume, 266 milliliters. Our temperature, we have to add 273 to make it in Kelvin. So this will be 298.2 Kelvin. Half the volume, 133 milliliters, over T2. Cross multiply, 266 T2 equals 298.2 times 133. Divide 298.2 times 133 divided by 266. So we get end up getting half of 298.2, which is 149.1 degrees Kelvin. If we want that in Celsius, we have to subtract that from 273. So in Celsius, this is negative 123 degrees Celsius. Here's the second problem. Calculate the potential volume of a gas contained in a 500 milliliter aerosol can when it is heated from 25 to 54. Try this one on your own. Press pause and then come back and watch the correct answer. We have Charles's law, V1 over T1 equals V2 over T2. V1 here, 500 milliliters. T1, 298 Kelvin, equals V2, and we need to get T2, so 54 plus 273, which is 327 degrees Kelvin. We're really not doubling the temperature, because on the Kelvin scale, this is not doubling the temperature, even though on the Celsius scale it would look like we do that. That's why we use the Kelvin scale to get the right relationships. Cross multiply, 500 times 327 equals V2 times 298. So 500 times 327 divided by 298 equals V2. Do the math. You get 548.66 milliliters. Significant figures here. We got three significant figures in the temperature, two significant figures in the temperatures. So I'll keep it at two significant figures in my answer. 550 milliliters. Now, assuming the pressure were held constant, you see it would need to take up a space of 550 milliliters. Now, because the space can actually change, it's actually becomes a relationship between volume and pressure, or between temperature and pressure. As the temperature increases, the pressure increases, and that's why it's so dangerous to heat up an aerosol can. So here we have our first two gas laws, Boyle's law and Charles's law. One's an indirect relationship, one is a direct relationship.